Hey everybody, Dr. A here, and in this video we're going to be providing some background information on gear systems, and we're going to conclude with a simple example of gears in mesh. So let's go ahead and get started. For our background information, we're going to say that gears in mesh are systems of two or more gears whose teeth are interlocked such that an applied torque will cause adjacent gears to rotate opposite of each other. One gear is the driver and the other or others is the driven. So in this little illustration here, we have a larger gear A that has a torque moment that is either applied to it or is transmitted to it. And what that's doing is that's going to cause the gear B that gear A is in mesh with to rotate in the opposite direction. So notice that gear A, which is going to be the driver in this illustration, is rotating clockwise, and then gear B, which is the driven, is going to then rotate counterclockwise in response to that. Now, there are a lot of relationships that we can use that will model gear behavior. And we're not going to get into all of that in this video. This is meant to be a video for mechanics of materials, introductory, to gear systems. It's not really meant to be a machine design class. So we're not going to get into all the details, but we are going to get into some. So the first thing we're going to discuss is a gear ratio, okay? Gear ratio. Now, this can be defined a few different ways. One way it can be defined as is the number of teeth in the driven gear divided by the number of teeth in the driver gear. So that's going to be the number of teeth in the driven gear, in this case B, divided by the number of teeth in the driver gear. In this case, this is gear A, all right? Another way we can define gear ratio is by angular velocity. This can be the angular velocity of the driver, which is gear A, divided by the angular velocity of the driven, which is gear B. So you see, if you look at these two relationships, they're inversely proportional, right? Gear B and gear B are it's in the numerator when you're ratioing the number of teeth, but in the denominator when you're ratioing the angular velocity. So these two ratios are inversely proportional to each other, okay? We could also express this as the gear speed of A divided by the gear speed of the driven gear B. Or we can express this as the gear diameter of B divided by the gear diameter of A. Okay, so all of these can define for us a gear ratio. And what's cool about this is if you have some of these pieces of information, they're all equal to each other, so you can relate them to each other and solve for other pieces of information. So let's write these variables down. N is the number of teeth in a gear, okay? All right, and then omega is angular velocity. S is gear speed. And then D is the gear diameter, okay? Another thing to note is, and I'm going to note this back up here next to our figures here, is that points of contact on meshed gears transmit equal magnitude forces in opposite directions, okay? So what does that mean to us? That means that the force that is developed, say, in gear A at this point of contact is going to be equal in magnitude and opposite in direction as the force that will develop at the same point here in gear B, okay? But the key there is equal in magnitude, opposite in direction, okay? And we're going to see an illustration of that here in our next part of this video. So I just deleted those vectors just so the figure still looks nice. So let's scroll down and let's get into a simple example of meshed gears. So in this example, we're being told to compute the torque in gear B. And we're being told that the radius of gear A is 6 inches and the radius of gear B is 3 inches. And then we see at A, we have an applied torque of 20 pound-feet. So if your initial guess is, okay, well, TB is also 20 pound-feet, that's going to be incorrect. And here's why. If we write the solution, I'm going to kind of zoom in on this point of contact here. And I'm going to say, okay, hey, we've got gear A here. And then we have the smaller gear B. And I'm going to zoom in here and kind of put some space in between these. This is gear B, all right? And so what's going to happen is you're going to have this tangential force that develops here. That's FA. And then at the same point on gear B, at that point of contact, you're going to have a tangential force FB that's the same magnitude as FA but opposite of direction. So that means that FA is going to equal FB. So what do we do with this? Well, we know that the definition of torque is force times radius, okay? So we're going to write here the torque at A is the force of A times the radius of A, which means we can rearrange this and we can say the force at that point of contact in A, in gear A, is going to be equal to TA over RA, the radius of A. So we're going to say that that's 20 pound-feet, and we're going to divide that by the radius of A, which was 6 inches or half of a foot. And what do we get here? We see the feet cancel, and we get a force, as you can imagine, 40 pounds, okay? And then what we finally want is this torque at B, right? So what we're going to say is the torque of B equals the force of B times the radius of B. But of course, the force of B is equal to the force at A, right? These are equal to each other. So what we're going to say here is this is just FA times RB. And so we're going to say that that's 40 pounds. And then just to be consistent with our units, I'm going to say 3 inches, but I'm going to say 0.25 feet. Okay, that's the 3 inches. And this is going to be 10 pound-feet. And this is my answer for the torque at B. So that's going to conclude this example. It's a pretty quick example, and it's going to conclude this video. Hopefully this little bit of information on gears and mesh was helpful to you. If so, please hit like and subscribe, and be on the lookout for other content similar to this. Thanks for watching.